These are the lesson activities for section 3.3 for differential equations. Consider the system below. Find the eigenvalues of the system by solving the characteristic polynomial, set equal to 0. Okay, so we find the determinant of a minus lambda I, so that's 2 minus lambda, 2, 1, 3 minus lambda. That's AD minus BC. Okay, FOIL this out and we get 6 minus 2 lambda minus 3 lambda is minus 5 lambda plus lambda squared minus 2. And that's lambda squared minus 5 lambda plus 4. And then we set that equal to 0. We solve it by factoring. This factors to lambda minus 4 times lambda minus 1. Set each factor to 0, and we get lambda equals 4 and 1. So there are our two eigenvalues. Next, we compute eigenvectors associated with each eigenvalue by solving A times V, which is an unknown vector xy, equals lambda V. So we'll use the lambda equals 4 first. Change this to system of equations, 2x plus 2y equals 4x. That is going to be solvable. It gives us some information. The other equation is either going to give us the exact same information or no information at all. So we can just use this one. Subtract 2x from both sides. We get 2y equals 2x. So x equals y. So we just choose any xy pair other than 0, 0. 0, 0 is never an eigenvector. That makes this equation true. So 1, 1 is a simple one. Then we do the same process for the other eigenvalue. So 2x plus 2y equals x. We'll solve for y. Okay, so 2y equals negative x. So y equals negative 1/2 x. So pick any eigenvector that satisfies that equation. So you can pick any xy pair except 0, 0. I like to have no fractions in my eigenvector, so I will choose x to be 2, and that makes y negative 1. Use each eigenvalue and eigenvector to write two solutions. So we've got y1 equals e to the lambda t v, and y2 is e to the other lambda t v. Okay, so use the two linearly independent solutions to write a general solution. So we have y equals k1 times y1, and y1 was e to the 4t 1, 1, plus k2 y2, and y2 is e to the t 2, negative 1. In the vector field, sketch the two straight line solutions we just found. So you sketch those by connecting the eigenvector we found to 0, 0 and making a straight line. So let's see, our eigenvector is 1, 1. And we make a straight line through the origin. That is associated with lambda equals 4. So the arrows point away, which is confirmed by the vector field. My other eigenvector is 2, negative 1, about right here. Connect that to the origin. And I'm going to do my best to draw the other direction here. Looks like that. And that is associated with lambda equals 1. and it's a positive lambda, so the arrows point away from the origin, confirmed by the vector field. And then I'm going to try to draw in a few other solutions. So it looks like they kind of all start at the origin and then sort of swirl out like that. And then this kind of goes like that. Okay, so what we should notice about this picture is that the solutions all leave the origin tangent to the eigenvector associated with the eigenvalue that's closer to 0. Okay, so all of these solutions I drew leave in a manner that it is tangent to the lambda equals 1 eigenvector. So they're all start tangent, and then they turn and end up parallel to the eigenvector associated with lambda equals 4, the one further from the origin. So this phase portrait is typical whenever you have two positive eigenvalues. When the solutions all leave the origin like that, we call the equilibrium point at the origin a source. Okay, consider the linear system below. Find the eigenvalues by solving the characteristic equation. Okay, so we take the determinant of 8 minus lambda, negative 11, 6, negative 9 minus lambda. That's AD minus B times C. So I multiply this out and I have negative 72 minus 8 lambda plus 9 lambda is positive lambda plus lambda squared, and then I have plus 66. Combine like terms, I have lambda squared plus lambda minus 6. We set that equal to 0 and solve. This is factorable, so I'm going to factor this to lambda plus 3 times lambda minus 2, set that equal to 0. And then you solve by setting each factor equal to 0, so we get lambda equals negative 3 and 2. So we find the eigenvectors by setting AV equal to lambda V for each of the two lambdas. I've set that up already. Then we change these two equations. So I have 8x minus 11y equals negative 3x. And the other equation is either superfluous or unhelpful. So we are just going to solve this first equation as long as it gives us some values that we can choose for x and y. Okay, so I want to get y by itself, so I'm going to subtract 8x from both sides. So I have negative 11y. Negative 3 minus 8 is negative 11x, so we get y equals x. So an eigenvector would be any xy pair that satisfies that equation except for 0, 0. So we put in 1, 1. And then you could have chosen 2, 2 or 3, 3 or any pair that satisfies y equals x. Okay, now we repeat the process for the other eigenvalue of 2. So I have 8x minus 11y equals 2x. I'm going to solve for y. 2x minus 8x is negative 6x. So y equals 6/11 times x. I'm going to make x 11 because of my personal preference to not have any fractions in my eigenvector, which means that my y value will be 6. Okay, my two solutions are going to be y1 is e to the lambda 1, so e to the negative 3t times the associated eigenvector. And then my other solution, y2, is e to the 2t times 11/6. To write the general solution, we just take a linear combination of the two solutions we have found so far. So we have y equals k1 times y1, which is e to the negative 3t times 1 plus k2 times e to the 2t times 11/6. Okay, in the vector field, we want to sketch the two straight line solutions. So one was 1, or 5, 5, or 10, 10, right? Any eigenvector that satisfied y equals x. We connect that to the origin. And that eigenvector was associated with lambda equals -3. So the arrows point towards the origin, which is confirmed by the vector field. My other eigenvector was 11/6. So I'm going to plot that point. 11/6 is like right here. It's a little too high. Okay, then I'm going to connect that to the origin best I can. Okay, I've gotten that one drawn in, and that was associated with lambda equals 2, which is positive, which means the arrows are supposed to point away from the origin, which is confirmed by my vector field. And then I'm going to plot several other solutions. Just pick some random initial conditions and follow the vector field. So it looks like they do something to the effect of that. And then put the arrows in that follow the vector field. And then in here, this kind of goes like that. Okay, that's a rough sketch, but that's the idea. So this phase portrait is typical whenever you have one negative and one positive eigenvalue. When the solutions around the equilibrium point behave like this, we call the equilibrium point a saddle. And these are the lesson activities, so I'm going to cross that out. Okay, find the particular solutions that satisfy the initial condition. Okay, so I've gone ahead and rewritten the general solution here. Now I just have to plug in a 0. And I get k1 times 1 plus k2 times 11/6 is supposed to give me 0, -5. And then I have two equations that I create from the top entry of each vector and the bottom entry of each vector. So this says that k1 plus 11k2 equals 0, and k1 plus 6k2 equals -5. So you can use your favorite method to solve a system of two equations with two unknowns. I am going to use elimination here by putting the second equation under the first, and I'm going to subtract the two equations. So my k1 minus k1 goes away, and then 11k2 minus 6k2 is 5k2, and 0 minus -5 is 5, which means k2 is 1. And then to solve for k1, plug the 1 in for k2, and k1 is -5 minus 6, which is -11. So those aren't the answers to the question. The answer is this function where you replace k1 and k2 with these two values. So my particular solution for this initial condition is going to be -11 e to the negative 3t times 1, 1 plus e to the 2t times 11, 6. Okay, so to summarize what we saw in the demo and the activities, if one lambda is negative and one lambda is positive, so lambda 1 less than 0 less than lambda 2, so you have a negative and a positive eigenvalue, then the equilibrium point at the origin is called a saddle. There are two straight line solutions in the phase portrait. The one associated with lambda 1, which I've said is negative, so it points towards the origin. And the one associated with lambda 2, the positive one, points away from the origin. And all other solutions come from and go towards infinity. Okay, if both eigenvalues are less than 0, they're both negative, then the origin is a sink. All solutions tend towards the origin, 0, 0, as time goes to infinity. Most solutions, other than the straight lines, begin parallel to the eigenvector associated with the eigenvalue that is further from 0, so lambda 1 in this case, the way I've defined it, and approach the origin tangent to the eigenvector associated with the eigenvalue closer to 0, which is lambda 2. Now, if lambda 1 and lambda 2 are both positive, both bigger than 0, the origin is a source. All solutions except the equilibrium solution go towards infinity as t goes to infinity. Most solutions leave the origin tangent to the eigenvector associated with the eigenvalue that is closer to 0. So that is lambda 2. And then they head out towards infinity in the direction of the eigenvector associated with the eigenvalue further from 0, lambda 1 in this case. A sink is called stable because any initial condition will always come back to the equilibrium point at the origin. Saddles and sources are called unstable because there are initial conditions arbitrarily close to the equilibrium point, the origin, but that move away. Okay, one more example. Let's consider Romeo and Juliet again. R prime equals AR plus BJ and J prime equals CR plus DJ. Let's say that both Romeo and Juliet are equally cautious and that they both get freaked out by their own feelings, and they are equally even more turned off by the enthusiasm of the other. So how could we name this romantic style? So their own feelings freak them out. So when they start to like somebody, that makes them pull away. And when someone else starts to like them, that also makes them pull away. So I don't know, we could call them a recluse, right? They just don't like to be in a relationship. What does your common sense tell you about the fate of their love affair? So if they both have this tendency to not want to fall in love, they don't like falling in love, they don't like other people falling in love with them, I would imagine that it's doomed, right? To capture the romantic style, we're going to describe all the constants. All the constants would have to be negative, okay? And B equals C and A equals D, but B and C have to be smaller because of this even more turned off, right? They're even more turned off by the enthusiasm of the other. So B and C model the enthusiasm of their partner, right? For Romeo, B is the coefficient on Juliet's feelings. For Juliet, C is the coefficient on Romeo's feelings. So B and C need to be the same, and A and D need to be the same value, but B and C have to be smaller than A and D, right? To show that this has a stronger effect on them. Okay, so we're just going to have A and D be -2 and B and C be -3, and we'll write it in matrix notation. So we have R prime, J prime equals the coefficient matrix times Rj. Okay, so Romeo is AR plus BJ. So A is -2, B is -3, and then C and D are going to be, okay, so C is -3 and D is -2. Use the tools of this section to sketch a phase portrait for the system and determine the fate of the love affair. Okay, so the tools are eigenvalue, eigenvectors, sketch a phase portrait. So my eigenvalues we find by taking the determinant of A minus lambda I which is AD minus B times C. So that's going to be 4 plus 2 lambda is 4 lambda plus lambda squared minus 9. Simplify this, lambda squared plus 4 lambda, -9 plus 4 is -5. Okay, that factors to lambda plus 5 times lambda minus 1. We set that equal to 0 and solve. We get lambda equals -5 and 1. So our phase portrait is going to look like a saddle. So we know that. And then let's just finish sketching the phase portrait by getting the eigenvectors. So we get the eigenvectors by setting AV equal to lambda V for each of the two lambdas. And we get -2x minus 3y equals -5x. Solve for y. So -3y. I'm going to add 2x to both sides. I get -3x. So y equals x. And so 1, 1 is an eigenvector. And then in my other eigenvalue, I have -2x minus 3y equals x. So -3y equals x plus 2x is 3x. So y equals -x. So 1, -1 would be an eigenvector. To sketch the phase portrait, I'm going to put in these two straight line solutions and start from there. Okay, so here is a phase plane, Romeo and Juliet on the horizontal and vertical axes. My first eigenvector was 1, 1, so that is about like this. And that was associated with the eigenvalue of lambda equals -5, which means that the arrows point towards the origin. Okay, then my other eigenvector was 1, -1, something like that. That's associated with lambda equals 1, so the arrows point away from the origin. And then the rest of the solution curves sort of follow the guidance of these straight line solutions. So pick an initial condition and it kind of follows the arrows on the straight lines. Okay, so we can say no matter what the initial condition, all of the solutions are heading off towards infinity, except when we're on the straight line solution associated with lambda equals -5. In that case, the solutions head towards the origin. Okay, so if Romeo and Juliet start, their initial condition is on this straight line, then their relationship will fizzle to mutual indifference. Right? Just goes to the origin where they both have 0 hearts for each other. Okay. But in every other case, their relationship is actually pretty explosive. If they start here, they end up in quadrant 2, where Romeo has negative hearts and Juliet has positive hearts. So here they end up with Juliet in love, but Romeo in hate. Okay. And getting ever stronger. And if they start anywhere on this solution curve, they end up with Romeo in love, Juliet in hate. If they start anywhere here, same, Romeo in love, Juliet in hate. That one also. And then if they start anywhere on this solution curve, they have the same outcome as this one. They land over here, Juliet in love, Romeo in hate. So in almost all initial conditions, they have a tragic love affair where one person falls in love and the other one falls in hate, and we have unrequited love. I don't know how to spell that word. Unrequited love. There is one initial condition where there's mutual indifference.